Hello there, ATS 211 students. Dr. Shragi here, and I am giving you a review session for our final exam. This review session is not going to have any video, it's just going to have audio because I know you guys want this material quickly, and embedding the video inside of the slides adds about an order of magnitude to the amount of time it takes the rendering of these videos to happen, so we're just going to do it using audio. All right, well, as I take a look at this stuff, it occurs to me that I have a review sheet and I have this final section. And this review session is not intended to in any way replace the review sheet or anything like that. This is to be complementing the review sheet. So you should definitely, make sure that you review the review sheet as well as this. I hope I'm being clear about that. All right, so anyway, we definitely covered plenty of material in this class to have a nice little final exam. And when we started coming back from spring break, the first thing that I noticed was we got talking about nor'easters. Because there was this stupidly named winter storm Stella. Hey, is that an official thing? Is that something that we actually care about, these names like Stella? But it was an example of a nor'easter, and I can certainly think of nice little vocabulary type questions I could ask you on the final about nor'easters, so make sure you know that definition and so on. Probably more relevant, though, to the purposes of the course, Stella was an example of what we called a bomb cyclone. What does it mean for a cyclone to be a bomb? Make sure you kind of review about that. The actual numbers about how it has to be a pressure fall of 1 millibar every hour for 24 hours is important. So make sure you know that kind of stuff. Perhaps more to the point, though, Stella was an example of a cyclone that was experiencing explosive cyclogenesis. Okay, all cyclones experience cyclogenesis as they are getting stronger, and then later a period of cyclolysis where they are getting weaker. What does cyclogenesis mean? What does cyclolysis mean? Like, during cyclogenesis, the pressure is falling, the circulation is increasing. During cyclolysis, the pressure is rising back towards average sea level pressure, and the winds are getting weaker and so on. Explosive cyclogenesis just means that it is happening particularly fast. All right, so let's see here. All right, so the main thing that happened on day 11, though, is not very testable, and that was we talked quite a bit about like different audiences for weather briefings and what they would want to know about and what they know going into a weather briefing and so on. And that doesn't really lend itself to a test very well. I think there were one or two multiple choice questions on the test. I mean, kind of just reviewed the slides from back in the day 11 presentation. But I mean, it's pretty basic stuff because I can't have you guys give a weather briefing or something like that at the final. But then we moved on to day 12 in the class, and we started talking about numerical models because, of course, numerical weather prediction models have become the main tool that we use in modeling, in forecasting. And, of course, a lot of the things that you guys learned about models and ensemble models and so on came from those COMET modules. And remember, I've decided that we're not going to actually explicitly ask about the COMET modules on the final, simply because you've already answered questions, objective questions about those modules. It doesn't seem necessary to test you guys on the same material twice. That doesn't very good teaching. So we're going to talk about models here, and I don't want to get just too bogged down in the differences between numerical models and statistical models or physical models and so on, in part because you learn more about that in other courses. But what fundamentally makes a numerical model, like the ones that we use to make forecasting numerical, is the fact that the model is it is based on the primitive equations, the physics that actually describe the processes that are at work. That's in contrast to like a statistical model, which is still using computations, but is just based on stats about the past performance of the weather or something like that. Or a physical model where you would be using something like a wind tunnel or something like that, where there was actually something physical you could touch. So the kinds of models that we're running, these simplified versions of the real system that we're trying to simulate, these models are all examples of numerical models, and they are based on the so-called 7 primitive equations, and which are listed here. And of course, I am not having any intention of you actually memorizing these equations or even labeling them or something. There's other courses in the curriculum where you do things like that. But the idea that these are the equations that actually describe the physics of the processes at work is what's key here in the numerical models. These equations are solved using the model's software is solving those equations on a grid. It divides the atmosphere up into a grid with it's a three-dimensional grid with some horizontal resolution and some vertical resolution. And those primitive equations are differential equations with respect to time. They are figuring out the time rate of change of temperature, of pressure, of winds, and all that kind of good stuff, vorticity, and so on, as a way of describing then what the weather is doing at some point in the future. In and of itself, that all makes good theoretical sense, and a mathematician would, would be happy with that answer. But the truth of the matter is, some of the terms in those equations are really awful. And to actually explicitly compute some of those terms would be pretty much impossible with a finite amount of computer time. And that's why we have to actually use approximations to the parts of those solutions. Those approximations are called parameterizations, and models are different from one model to another, in part because we choose different parameterizations from one model to another. It's an active area of research to come up with these kinds of approximations that work better under certain circumstances than others, and so on. And so the team that developed the GFS model, or the WRF model, or the ATA model, or the ECMWF model, they make choices about what they want to use for parameterizations. Just to give an example of what I mean by a parameterization, because I know this is a term that students often get kind of bogged down on, keep in mind that, like, for example, we talked about things like the flux of heat from the surface of the Earth. Conduction, basically. Turns out conduction is a wildly complicated thing to make a forecast of. Actually, how much heat is being transferred from the warm ground into cooler air that's right above the ground is a very complicated thing. You have to know things like soil moisture and soil roughness and leaf area index and all kinds of parameters that we don't necessarily know, or certainly don't forecast, or certainly don't give to the models, or don't necessarily observe. On the other hand, a fairly simple equation, a parameterization that behaves very much like the true physics of the situation, is the so-called bulk parameterization. The bulk parameterization is this little term that I have here on this particular slide, where the flux of heat at the surface, FHS, is a simple equation that's just CH is a constant, V is the wind speed, and TS minus T air is the temperature of the surface itself minus the temperature of the air. It's basically the difference between the temperature of the ground and the temperature of the air. See how this is just a simple little product of three terms? And it turns out this is a good ballpark estimate of the amount of heat being transferred by conduction from the ground into the atmosphere, without getting all bogged down in exactly how rough the surface is, and exactly how moist the soil is, and how dense the air is, and things, a million little factors that affect it. So this is a simplification. We can solve this relatively simple equation much more easily than the true physics of the situation. That's what we mean by a bulk parameterization. And every model has to make, the people who develop it have to make choices about what parameterizations they want to use. That's part of the reason why we have to have a large number of models, is they all work differently. They all have different resolutions, both horizontally and vertically. They have different time steps, they have different domains, and they have different parameterizations, how they choose to make approximations to the true solution. All right, so day 13, moving on, was a comment module. Again, it was interesting and important stuff, but you've already been assessed on that, so I don't need to do that a second time. That would be bad teaching. All right, then we moved on in day 14, and we started talking about waves in the atmosphere. And in particular, I mean, don't get me wrong, if this was a class in dynamics, we'd get all bogged down into gravity waves and inertial gravity waves and sound waves and shallow water waves, and I mean, that would be all really thing. But in a class that's more about weather analysis and forecasting, we want to focus on the main one that has to do with synoptic scale weather, which are Rossby waves. And the main thing about Rossby waves, or planetary waves is another word, is that these are the troughs and ridges in the flow. Strictly speaking, some troughs and ridges are not true Rossby waves, but they're all well approximated by Rossby waves. And they are these troughs and ridges that we get excited about when we look at upper tropospheric flow. And strictly speaking, they are caused by the conservation of absolute vorticity in the atmosphere. That means, of course, that you do need to review what we mean by absolute vorticity, but that's not such a difficult definition there, how it's just a sum of the Coriolis parameter and relative vorticity at any given time. And we actually kind of walked through a fairly straightforward derivation, kind of there was no math. I mean, we were just sort of working with symbols and things like that, and diagrams on a PowerPoint slide. But we were able to demonstrate, for example, that Rossby waves have to propagate westward with respect to the flow itself. From the point of view of any given air parcel, the trough or the ridge is shooting off to the west. They have to for a Rossby wave. So like on this slide that I have here, the blue dots indicate the position of like troughs and ridges in the flow or air parcels in the flow or whatever at one time, and then the red spots are, maybe 12 hours later or something, and you can see how the pattern of the trough and the ridge has shifted to the west. All with respect to the flow, all Rossby waves have to propagate to the west, but with respect to the ground, it gets more complicated, because then with respect to like an observer on the ground, well, the Rossby waves might be propagating westward or eastward. Well, because that depends to a certain extent on the speed of the flow that is translating those troughs and ridges eastward, and about the wavelength of the Rossby wave. Because remember, the short waves of the Rossby waves barely move at all westward, and the long waves of Rossby waves are shooting very fast westward. Well, then, depending on the speed, the size of the wavelength of the wave, we add that to the mean speed of the wind, and we get that these waves are traveling at different speeds to the east. Now, notice, though, that this business of being attached, the speed of propagation of these Rossby waves depends in part on the fact that they have different wavelengths. There are short waves and there are long waves in Rossby waves, and because their phase speed depends on their wavelength, we describe Rossby waves as being dispersive. This is an important vocabulary word. Anytime the phase speed of a wave depends on its wavelength or other properties of the wave like frequency and so on, the right vocabulary word to describe them is dispersive. That's in contrast to non-dispersive waves. The classic example used in teaching of non-dispersive waves are sound waves. Regardless of the wavelength of a sound wave or its frequency or anything like that, all sound waves move at the same speed. In a given medium. Obviously, like the temperature and the density of the air and things like that make a difference. But in a given medium, things like wavelength and frequency and so on don't make any difference, which is good for listening to music, for example, right? The high notes and the low notes are traveling, those waves, sound waves are traveling at the same speed. It would be hard to listen to music if the tuba sounds got to you before the flute sounds did. And it would be hard to make the music sound right because the notes that were played at the same time would get to you at different times. Fortunately, that's not the way sound works, but it is the way Rossby waves work and other types of waves in the atmosphere. Because we are adding the phase speed of the Rossby wave itself to the large scale speed of the flow around it that is translating the whole trough and ridge system eastward, it turns out that short waves appear to move very fast to the eastward, whereas the long waves tend to be either stationary or even retrograde, as in they tend to actually even slowly propagate westward. Again, a long wave its phase speed is very fast to the west. So when you add that to flow from the west, you end up with a speed with respect to the ground of these long waves as being either stationary or even slightly retrograde. Troughs and ridges are really cool, and even in like the ATS 113 class, we spend a lot of time talking about troughs and ridges and what they tell us about what's going on in the atmosphere and so on. But a bigger question is, why do they even happen in the first place? And it turns out there's two main mechanisms that create troughs and ridges in the atmosphere, and they are an example of a type of instability. This isn't the way we tend to use the word instability when we're talking about the atmosphere. We tend to get excited about instability in the context of thunderstorms. But this is another sense of the word instability, where we're talking about the growth of troughs and ridges. There's all kinds of little disturbances in the flow that make the flows, swing north or swing south. The question is, will that grow into the form of a trough or a ridge or not? One mechanism by which Rossby waves, in fact, the only mechanism by which true Rossby waves form, is by barotropic instability, although we're going to fold baroclinic instability and say that's close enough. Strictly speaking, those are not exactly Rossby waves, but they behave like Rossby waves. They're equivalent in some ways. Anyway, barotropic instability is a type of instability in the Earth's atmosphere that has nothing to do with temperature gradients or density gradients or anything like that. It's just about the fact that Coriolis parameter changes with respect to latitude. And because Coriolis parameter changes as a function, it goes from 0 at the equator to large at the North Pole, it has a rate of change of the Coriolis parameter. And we actually worked through some examples that of all places I got from the ATS 113 teacher's stuff. where we showed how conservation of absolute vorticity means that if F is changing, the Coriolis parameter is changing, we have to have corresponding changes in the relative vorticity, and this sets up troughs and ridges in the atmosphere. Now, as it happens, this barotropic instability, this rate of change of the Coriolis parameter with respect to latitude, happens to be greatest in the tropics and the subtropics. So that's just the math of how it works out as to where the biggest changes in F are. So, well, this tends to be a really good way of explaining the presence of troughs and ridges at relatively low latitudes, in particular the ones in the subtropical jet stream. Subtropical jet stream is at like 25 degrees north, maybe 30 degrees north overall. That's a relatively straightforward way to explain that phenomenon. Well, stuff about the subtropical jet is interesting, but that's certainly not the main bringer of weather to our part of the country. Clearly, we're more interested in phenomena that happen on the mid-latitude jet stream. Now, the processes that lead to the formation of troughs and ridges on the mid-latitude jet stream are strictly baroclinic instability, not barotropic instability, although they're closely related phenomena. Basically, baroclinic instability is the same thing as barotropic instability. You're just adding also a conservation of potential vorticity phenomenon that happens along a frontal boundary in the presence of strong temperature gradients. This is not really the best class to actually learn how that all works. The basics of how baroclinic instability produces troughs and cyclogenesis and so on, that's better handled in like Dynamics 2, where we really take apart all the processes that lead to cyclogenesis and so on. So we're going to leave that on kind of there as just another example of how troughs and ridges can form. In the mid-latitude jet stream, it is a combination of a barotropic instability associated with the changes in the Coriolis parameter with respect to latitude and the processes that happen along the front. Okay, in and of itself, that is as far as we need to take that there. Now, on the day 15, yes, we had a comet module. Again, there's no particular reason for me to give you another test on that. Okay, that's not the best way to move forward on all of this. Okay, now since we had been talking about baroclinic instability and barotropic instability, that gave us a good way on day 16 to segue into learning more in general about stability and about how stability is about a tendency of a system to accelerate away from its current state or to resist accelerating away from its current state. And we could talk about that in terms of like a stack of books or any number of different systems, but of course in meteorology what we care about is static stability. Static stability is the one that's associated with, well, mostly we care about it because of thunderstorms and so on. Although there are applications for static stability in the context of turbulence, and there's applications of static stability in the context of wind power, and so on. But clearly in a class about weather analysis and forecasting, we're most interested in it in the sense of developing thunderstorms and so on. Static stability, it's important to remember, is a property of a layer of the atmosphere. It's not a property of an air parcel or anything like that. It's a property of layers of the atmosphere. So you could talk about the static stability of the layer from 1,000 millibars to 850 millibars or whatever. Static stability changes, and that's why we have to take measurements of the atmosphere using radiosondes and weather balloons and so on. Because from time to time, from one time to another or from one location to another, clearly the static stability of different layers is changing. Now then, on that day 16, we hit a stretch of about, I don't know, maybe 30 slides or something like that took a whole careful analysis just to make sure you, at least in a graphic sort of way, understood what static stability meant for a layer of the atmosphere. And how when we displaced a layer, an air parcel rather, that was in a layer that was statically blank, like statically stable or statically unstable or statically neutral, well, then we could ask ourselves, what was the buoyancy on that air parcel? Once we displaced that air parcel vertically in an unstable layer, was it positively buoyant or negatively buoyant for that air parcel? Was that air parcel accelerating upward or downward after that on its own, etc.? Make sure you can, and that's classic stuff that I can easily write multiple choice questions about. Okay, so make sure you can work your way through all that kind of stuff that we did on day 16. Okay, let's see here. using those kinds of processes there to understand that we kind of in a very informal way sort of graphically derived these three inequalities where we were comparing the environmental lapse rate to the dry adiabatic lapse rate. The symbol we used for the dry adiabatic lapse rate here was gamma D, whereas gamma was the measured environmental lapse rate in each of these layers. Make sure you understand how we get these three different inequalities. Like if I gave you a question that was comparing the environmental lapse rate to the dry adiabatic lapse rate, what could you say about the static stability of that layer? All right, now that business of the environmental lapse rate then kind of is a measure of static stability, but it turns out not to be a particularly convenient one. There's actually a number of reasons why that's not your best choice of a measure of static stability. So then we started talking about all the different ways we could quantify static stability of the atmosphere, and they're all awesome. I mean, lifted index, the K index, the total index, the Showalter index, etc. They're all very cool. But they're not exactly the kind of thing that lends itself to a final exam. Frankly, they're difficult to even do in a college-type teaching situation just because they're so regional. Any kind of thresholds I would have told you about, like what's a good value of the lifted index for thunderstorms, well, that very much depends on what part of the country you're in, what altitude the station is at. It depends on things like what time of year it is, etc. It's not really college material to memorize those kinds of thresholds. That's more the kind of thing you would learn as part of your training at a job or something like that. So we're not going to get stressed about like those actual values or what any of those indices mean so much as we went through and talked about how all of them exist and so on. But one of them was more important, and that was CAPE, but we'll come back to that. That wasn't the order in which we talked about these things. First of all, I wanted to talk about how all these static stability indices can change. Because, I mean, for example, we tend to take our observations twice a day up aloft. One observation is about 6 in the morning and one's about 6 at night in our part of the country. Well, at 6 in the morning, the atmosphere is not all that unstable. And by 6 o'clock at night, afternoon thunderstorms have already happened. Clearly, we need some way of taking the information that we got from that early morning sounding and moving forward with that and figuring out how the static stability will change over the course of a day. And we ended up actually with 4 different mechanisms as to how static stability can change. Now, they're all, though, really about how to change the environmental lapse rate. I mean, basically, that is what all of these mechanisms are doing the dry adiabatic lapse rate is a constant. We can't do anything about it. It's a physical constant of the atmosphere. C sub P over G, or is it G over C sub P? I always forget which way it is. But I mean, it's 2 physical constants of the atmosphere. We don't have any control over that. But we can, of course, adjust the environmental lapse rate by a number of meteorological processes. And, well, 2 of those mechanisms are not really all that shocking. It's just finding the actual mechanism by which they would happen. I mean, clearly, if we wanted to change the environmental lapse rate, one way would do it be to heat the bottom of the layer, and another way would be to cool the top of the layer. Both of those would make the layer less stable. Now, it takes a little bit of doing to think about how those things would happen. I mean, heating the bottom of the layer typically means letting the sun shine onto the ground, where the ground then will warm up, and then by processes like conduction, warm the air below, at the bottom of the layer. Or by cooling the top of the layer, which is a little harder to think about. In practice, that's usually some kind of like cold air advectional loft, like maybe associated with a trough or something like that. But okay, once you kind of think it through, clearly these are not terribly hard to imagine, and in fact they happen all the time. For example, the business of the production of thermals, the rising and sinking plumes of air that happened on an ordinary sunny day, is clearly associated with this idea of warming the surface of the earth. We get these rising and sinking motions that are happening on their own, they're free convection, because of the changes in the stability of the layer of the air near the surface. That in and of itself is not so hard to think about. Now, it gets to be a little bit more tricky to think about a way to change the environmental lapse rate through the process of mixing, whereas layers of the atmosphere are churned by turbulence or by flow over obstacles or whatever, we can cause the layer of the air to mix, and mixing can change the environmental lapse rate and therefore the static stability of the air. Now, how it actually happens has to do with the fact that as we mix air
conserved properties of the atmosphere become evenly distributed throughout that layer. One such property being potential temperature, a property we did not spend any time on this semester. But potential temperature being constant with respect to height is another way of saying statically neutral. So by mixing the potential temperature of the air evenly through a layer so that it change in potential temperature with respect to height is zero, that is what statically neutral means. Or that is how the environmental lapse rate approaches the dry adiabatic lapse rate. How exactly that mechanism happens, what potential temperature is, that's kind of all something you need to take physical meteorology to have gotten the details of. And we can do that in a different semester or whatever. But the idea that mixing makes a layer of the atmosphere statically neutral is a good point because, well, most of the time layers of the atmosphere are maybe a little bit stable. Okay? The normal situation in the atmosphere is to be slightly statically stable. Otherwise, there'd be thunderstorms happening all the time. Well, if the atmosphere starts off statically stable and then mixing causes it to approach statically neutral, that's becoming less stable. So mixing layers of the atmosphere is a powerful way to get the environmental lapse rate to become less stable under most circumstances. Now, this doesn't tend to be the mechanism that causes thunderstorms or something like that, but this does tend to be the mechanism that produces certain kinds of turbulence in the atmosphere, that has certain effects for energy production and so on. It's an important process. It just isn't necessarily the one that leads to thunderstorms. A key way that thunderstorms can happen, however, is associated with our fourth and final mechanism that causes changes in the environmental lapse rate, and that's about lifting and lowering layers of the atmosphere. Remember, as we lift and lower layers of the atmosphere, the difference between the pressure at the top and the bottom of the layer stays the same. If this layer of the atmosphere is 100 millibars thick, it will still be 100 millibars thick if we lower that layer, or it will still be 100 millibars thick when we lift that layer. But because of the compressibility in the atmosphere, that doesn't mean that the top and the bottom of the layer are the same distance apart. As we lower a layer of the atmosphere, the top will move farther than the bottom of the layer does, as you can see in this slide that we have here from day 17. Or if we lifted the layer, you can just reverse those arrows on that little diagram there. You can see that the top of the layer moves more than the bottom of the layer. And since our dry adiabatic lapse rate is the change in temperature with respect to distance, moving the top of the layer more than the bottom of the layer means that the top of the layer has a bigger temperature change than the bottom of the layer does. And therefore, there's enough resulting change in stability. As it happens, you can work through the math of it all and show that lifting a layer always makes the layer less stable, and lowering a layer always makes it more stable. And this has got a lot of different applications in the atmosphere. The processes of making a layer of the atmosphere more stable by lowering it is actually a big part of the reason why, like, high pressure systems are stable, why you don't get thunderstorms under high pressure systems. The large-scale sinking motion in the anticyclone is making the layers of the atmosphere more and more stable. For that matter, if I go over here to this next slide here, this business of lifting layers of the atmosphere as a way of making them less stable and more conducive to the formation of thunderstorms, I mean, this is the real reason why low-level convergence, like what happens in the intertropical convergence zone, where low-level convergence at the surface causes layers in the atmosphere to rise, or for that matter, the center of cyclones or something like that, where low-level convergence is forcing layers of the air to rise, or for that matter, on, say, out ahead of a warm front, where layers of the atmosphere are overrunning and rising. But this is, or upper level divergence, I'm just thinking out loud here now, upper level divergence, like in the front left and right rear quadrants of a jet stream. All of these things cause layers of the atmosphere to rise, and they become less and less stable. They are resisting the formation of thunderstorms less. Okay, cool. Now, if you're going to be talking about stability, you just can't go through it in meteorology classes without talking about CAPE, or convective available potential energy. Remember, that is the potential energy that exists in the column of the atmosphere that could be released in the form of an updraft of a thunderstorm if a thunderstorm happened. We are converting the potential energy of the mass in the vertical column of the atmosphere into kinetic energy of an updraft. Now, to come up with an estimate of this, or at least like a visual approximation to how great the CAPE is at any given time, remember we have to use QT diagrams. and I think you guys are fairly comfortable. You're not going to be working with a skew-T diagram in and of itself on any questions on this, but you might be answering questions about how something is done. And one of the processes you have to be able to think about is how we compute the lifted condensation level, which was like the cloud base. We lifted the air parcel dry adiabatically until it became saturated. And as we lifted these air parcels beyond that height, we had to talk about how they were being, the temperature was decreasing now at the moist adiabatic lapse rate. And as that air parcel is now rising further, we're forcing it to rise ahead of a cold front or to rise over terrain or whatever. If we are forcing it to rise, at some point it'll hit its level of free convection, the height at which now that air parcel is as warm or warmer than the environmental air around it, as determined by the radiosonde and weather balloon. And if that air parcel can be deadlifted all the way to the height of the level of free convection, now, as indicated on like these kind of graphs here, you can see how the temperature profile of the air parcel is to the right of the environmental air parcel. It is warmer than the air parcel. It is positively buoyant, and it'll rise on its own all the way to the level of zero buoyancy, which is up, in this case, up near the tropopause, where the air parcel is now again as cold or colder than the environment around it, and it's now negatively buoyant and so on. Cool. Now, again, I'm not going to have you do that on a graph. Okay, that's just not a straightforward thing to ask on a multiple choice question on blue line. But what you notice here is how this bounds, this creates boundaries that are our cape. The cape is this positive area that's bounded on the top and the bottom by the level of free convection and the level of zero buoyancy. The places where it has positive buoyancy, and the area between the air parcels curve and the environmental temperature profile is proportional to the cape of the area. Cape is a quantity. It's actually from an integral that's performed in here. It has units of like joules per kilogram. How many joules of kinetic energy will the air parcel have per kilogram of the air parcel? But the actual evaluation of this integral is wildly complicated. Let software do that for you. But to just visually approximate it, you can see it on this area like this. So cape is the so-called positive area between the level of free convection and the level of zero buoyancy. That's in contrast to sin, or convective inhibition, the negative area between the surface and the level of free convection. This is the area of the temperature profile where the air parcel that we are lifting is actually still colder than the environment around it. We haven't had enough latent heat release yet in our air parcel to make it warmer than the air around it. So at these altitudes, inside of, below the level of free convection, our air parcel is actually still colder than the air around it. If we stopped lifting that air parcel, it would sink back down to the surface. Now, that means that convective inhibition is something that has to be overcome if we're going to get thunderstorms. We have to lift an air parcel from the surface all the way to its level of free convection. Doing so takes a certain amount of work, a certain number of joules per kilogram of air that we're lifting, hence sin is very analogous to cape. It is an amount of work we have to do to get the air parcel to the level of free convection. Two pieces of information then that we can quickly get about on a skew-T diagram that tells us something about the stability of the atmosphere. Once you start talking about cape, you start heading in the direction of the energy helicity index, so we got to talk about helicity to get there. Helicity is another type of rotational motion in the atmosphere. We already talked about relative vorticity, absolute vorticity, planetary vorticity. We even briefly mentioned potential vorticity. Helicity is a very similar idea, except the axis of rotation is different. Relative vorticity is by definition with respect to a vertical axis, whereas helicity is by definition with respect to a horizontal axis. So think of the rotation in helicity as being kind of like, think of the rotation of like a Ferris wheel or something like that. It's rotation where the axis of rotation is horizontal. Now, we can produce helicity in the atmosphere based on like vertical wind shear and so on. There's different processes in the atmosphere that produce helicity, and it is something that we measure. It's something that we get from the wind observations that come in from a weather balloon. But helicity in and of itself doesn't do anything interesting in the atmosphere. It's only the fact that we can convert helicity into relative vorticity in the updraft of a thunderstorm via the process of tilting. Tilting is one of the terms in the so-called vorticity equation that is about changing helicity of the environment into relative vorticity. And you can kind of see on this diagram, you kind of get a sense of it. See how there's like those little rolling motions in the environment around the thunderstorm, but then the updraft of the thunderstorm kind of tilts those vortex tubes so that they have a vertical axis instead of a horizontal axis. That mechanism is called tilting. Different thunderstorms are more or less efficient at producing relative vorticity in this way, but it is an important process with regard to tornado genesis because tornadoes clearly have a lot of relative vorticity, right? They are rotation around a vertical axis. Now, as it happens, tilting is not efficient enough to produce all the rotation that you see in a tornado. Turns out there's just never enough helicity in the environment, and tilting is not an efficient enough process to produce all of that rotation. But part of that will also be about enhancement of relative vorticity via the so-called stretching term. The stretching term is another term in the vorticity equation that is, I'm just actually fixing something on one of your slides here. Hold on, there we go. You'll see it better when you get to your presentation there now. All right, so the stretching term has to do with the updraft of the thunderstorm. Updrafts stretch as they go up. Remember, at the bottom of the thunderstorm, the updraft is relatively slow, and as it is experiencing more and more upward acceleration as it goes up, as it goes through the positive area of the cape, you get stretching as it's going faster and faster. The bottom of any given air parcel is moving slower than the top of the air parcel and stretches. That all is mathematically represented in the vorticity equation because stretching enhances relative vorticity. Again, this is not dynamics 2. In dynamics 2, we'll actually take that apart and actually analyze what does that mean? How do we get stretching to produce more relative vorticity? But it turns out stretching and tilting combine to provide enough rotation to have favorable tornado genesis. But notice what that tells us. That tells us you need both. You need helicity in the environment, something we can measure from observations, and CAPE, which is going to provide us the updraft of a thunderstorm, assuming a thunderstorm happens. And that's kind of the rationale behind this very exciting energy helicity index, or EHI. It is the product of CAPE and helicity. Now, in practice, EHI is defined to be the product of CAPE and helicity and then minus this constant. Okay, I didn't make the invention. It just makes the number smaller and easier to work with. But it gives you this idea that to have tornadoes, you need both. If you're going to have an outbreak of tornadoes, you are clearly going to need both a good source of helicity in the environment and a good updraft that can both tilt the helicity into the thunderstorm and stretch the newly formed relative vorticity to accelerate it to be enough rotation to have a tornado. That's really cool stuff. All right, now days 19 and 20 in the class, again, were just comment modules that we don't need to worry about for the final. You've already been assessed about them. And finally, day 21 was the touchy-feely kind of thinking about the future. This is a capstone experience for some of the students, etc. All right, so those days aren't conducive to testable material, and frankly, there's no shortage of material already on this test. I've written the test already, and in its current draft, it's, I think, 32, something like that, multiple choice questions. I'll probably tweak it a little bit before I post it. But it's all multiple choice that comes from the review sheet and this review session. I think that you've got the information that you need now to be well prepared for it. Keep in mind it is something of a capstone. It kind of integrates, especially the intro class, into our understanding. You're going to be well prepared if you've worked your way through the review sheet and you've worked your way through this review session. But no matter what, you need to get that test done sometime during finals week. I'm going to set a deadline of Friday afternoon for that final. If you have any questions as you are preparing for this, I certainly understand. It's been a bit of an informal semester, and if you have questions about the test or questions about some of the material, I'll completely understand. Just get a hold of me, and I'll be glad to talk to you about whatever you need. And all right, best of luck with the final. All right, talk to you guys later.